Close your eyes now and drift back with me, back through the river of time itself. In the beginning, there was only fire, a single point containing everything, exploding into existence with light flooding reality and heat beyond imagination. The universe was born in violence, yes, but from that chaos came something extraordinary. We watched together as the first minutes unfolded, particles dancing into being, the laws of nature carving themselves into the very fabric of space. Then came the darkness, a long, silent darkness where matter drifted unseen through an endless ocean of nothing. But gravity was patient. Gravity was weaving its invisible threads. And then the first stars ignited, brilliant beacons tearing through primordial hydrogen, bringing the cosmic dawn. Galaxies began their slow, chaotic assembly, colliding and merging in a universe still learning how to exist. Now something changes. Now we arrive at a different time, a quieter time. 2 billion years have passed since the beginning, perhaps 6 billion, and time moves differently out here in the cosmic deep. The frenzied pace begins to ease. The universe has passed through its turbulent adolescence. The violent storms are calming, and now the cosmos enters what we might call its golden period, an era of remarkable stability and steady growth and patience. This is not a time of explosions or catastrophe, though they still occur drifting somewhere far away. This is something more subtle, more profound. The universe is learning how to build things that last, stars that burn steadily for billions upon billions of years, galaxies taking on elegant forms that will endure, conditions emerging that will one day allow planets to form, chemistry to flourish, perhaps even consciousness to stir. The cosmos is slowing down, taking a deep breath, and in that breathing space, everything we know today begins to emerge. Imagine drifting through an endless garden of light, where everywhere you look there are stars. Not the violent giants of the early universe, but something different now, something softer. The universe is learning a new way to make stars, a better way. A way that speaks of patience rather than urgency. In the beginning, stars were reckless and massive, burning themselves out in cosmic heartbeats, living fast and dying young in brilliant explosions. They were phoenixes consuming themselves almost as quickly as they were born, spectacular but unsustainable. But now the cosmos discovers patience, and with each generation the ingredients change in subtle but profound ways. The first stars exploded and scattered new elements into space: carbon, oxygen, silicon, iron, and these elements, though still rare, act like cosmic coolants in the star-forming process. When clouds of gas collapse under their own gravity to form new stars, the presence of these heavier elements allows the clouds to radiate away their heat more efficiently, and cooler clouds can fragment into smaller pieces before collapsing, naturally leading to the formation of smaller stars. And smaller stars, remarkably, burn for a very, very long time. The universe is filling now with gentle, steady lights, stars similar to our own sun and some even smaller, red and dim and patient. These stars will shine not for millions of years, but for billions, some for trillions. A star born during this golden age might still be burning today, more than 13 billion years later, And it will continue burning long after we are gone, long after everything we know has faded. This is the gift of patience, the universe learning that longevity matters more than brilliance. Let yourself drift through a spiral galaxy's arm and feel the gentle warmth from countless stellar nurseries, vast molecular clouds dozens of light years across, pregnant with stars about to be born. Here in the darkness between existing lights, new stars are forming through a process that has become organized and efficient. Gravity compresses matter slowly, ever so slowly, until finally deep in the hidden core nuclear fusion ignites, and a newborn star takes its first breath of light. And it will breathe steadily for epochs beyond counting, providing stable energy to whatever might develop in the space around it. Star formation has become organized now, efficient in ways it wasn't before. Along the spiral arms of maturing galaxies, density waves move like ripples on still water, and gas clouds drift into these waves, compress, collapse, and give birth to new stellar generations. The massive blue stars, those brilliant giants, still form occasionally, lighting up the spiral arms with their fierce blue-white glow, but they are no longer the norm. They are temporary, brief fireworks, spectacles that fade quickly on cosmic timescales. It is the smaller stars, the dimmer ones, that tell the real story. Sun-like stars, orange K-type stars, red M-type dwarfs, these quiet citizens will form the backbone of every galaxy. They will outlive empires, outlive galaxies themselves in some cases. Different galaxies birth their stars differently, creating a cosmic diversity. In grand spirals, star formation continues along those elegant arms, a steady conveyor belt of creation, consuming gas and recycling material from dying stars while maintaining enough fuel to continue the process for billions of years. These galaxies achieve a sustainable balance, neither exhausting their resources too quickly, nor remaining sterile and inactive. But in elliptical galaxies, those smooth, featureless balls of starlight, most of the star formation has already ended. These galaxies consumed their gas in violent bursts during their formation, triggered by the mergers and collisions that created their peculiar shapes. Now they are settling into quiet old age, their stellar populations aging together like residents of a cosmic retirement community, with few new stars being born to replace those that fade. They have become the retirement communities of the cosmos, places where the drama has passed and only the long, slow decline remains. And as stars continue to form and die across the universe, something profound happens with each cycle. Each generation enriches the universe with new elements, heavy elements forged in stellar cores and distributed through space by dying stars. Massive stars forge oxygen, neon, magnesium in their cores, and when they explode as supernovae, they scatter these elements across vast regions of space. Smaller stars, like our sun, create carbon and nitrogen through their internal alchemy, and when they die more gently, shedding their outer layers in beautiful planetary nebulae, they distribute these gifts more peacefully across their cosmic neighborhoods. The universe is becoming chemically richer with every passing generation, and this enrichment is not merely an accumulation of new elements, but a fundamental transformation of cosmic potential. With every stellar generation, there are more building blocks available, more ingredients for complexity. Them's communion or UVs, ormporn for organic molecules, oxygen for water, nitrogen for amino acids, iron and silicon and magnesium for rocky planets, all these elements become progressively more abundant throughout the universe during this golden age. The cosmos is learning how to make worlds like Earth, places where chemistry can become intricate and diverse. This golden age of star formation fills the universe with steady, reliable lights, lights that will burn long enough for something remarkable to happen nearby, long enough for planets to form and cool, long enough for oceans to gather on their surfaces, long enough for chemistry to become intricate, long enough perhaps for life to emerge and evolve. But we're getting ahead of ourselves. For now, simply drift among these newborn stars, feel their warmth and their patience, their gentle, unwavering glow spreading across the darkness like lanterns in an infinite night. The typical star-forming region during this epoch has achieved a kind of equilibrium, a balance between the forces that create stars and those that regulate their formation. Within giant molecular clouds, turbulence creates dense knots where gravity can triumph over the supporting pressures of magnetic fields and thermal energy. These dense cores collapse over hundreds of thousands of years, heating gradually until their centers become hot enough to ignite hydrogen fusion. The moment of ignition marks the transition from protostar to true star, from an object heated only by gravitational contraction to one powered by nuclear reactions in its core. This is the universe breathing slowly, creating lights that will last, creating the conditions for whatever might come next. The chemical enrichment proceeding during this era is not uniform across all regions, creating a kind of cosmic geography of metallicity. Regions where star formation has been most sustained show the highest levels of heavy elements, while more isolated regions retain compositions closer to the primordial mixture of hydrogen and helium. This variation adds texture to the cosmic landscape, creating environments of different potentials. The star formation during this golden age also shows remarkable structure at the largest scales, with environmental factors playing crucial roles in determining where and how stars can form. Within galaxy clusters, the hot intracluster gas can sweep away the cold gas reservoirs of infalling galaxies through ram pressure stripping, quenching star formation and creating a segregation between actively star-forming galaxies in the outskirts and quiescent galaxies in the dense cores. This creates patterns visible across the universe, patterns that tell stories about environment and evolution. The typical star-forming galaxy during this golden age is magnificent, its spiral arms glowing with the combined light of massive young stars embedded in or recently emerged from their natal clouds, while countless smaller yellow stars burn steadily in the background. The majority population that will carry the galaxy forward through billions of years. Interspersed among the bright blue regions are darker lanes of dust, the raw material from which future generations will form, creating beautiful contrast in the galactic landscape. The legacy of this golden age extends directly to our own existence, for the Sun itself, born some 4.6 billion years ago, is a child of this era's later stages, formed from gas already enriched by multiple generations of stellar evolution. Every atom in our bodies heavier than hydrogen was forged in stars born during or before this golden age, processed through stellar cores and supernova explosions, then incorporated into the molecular cloud from which our solar system formed. We are quite literally the descendants of this era, made of star stuff, as Carl Sagan memorably observed. our very existence dependent on the nuclear alchemy that occurred in countless stellar furnaces during this productive and transformative epoch. This is the universe breathing slowly, creating lights that will last, establishing the foundations upon which complexity can build, filling the cosmic darkness with gentle, steady glows that will endure for billions of years, patient lights waiting to see what might develop in their vicinity. Something beautiful is happening across the cosmos, something that unfolds so slowly you might miss it if you blinked on galactic timescales. But the transformation is profound. The chaos is settling, and after billions of years of turbulence, collisions, and mergers, galaxies across the universe are finding their final forms like dancers discovering their rhythm or water finding its level. This transformation unfolds over billions of years, driven by forces both elegant and invisible, gravity, rotation, the gentle dissipation of energy through various processes. What emerges from this slow settling is breathtaking in its variety and beauty. Close your eyes and picture a spiral galaxy, vast and majestic, with arms sweeping outward from a glowing core in graceful curves that seem to suggest motion frozen in light. This is not how galaxies began. The first galaxies were small, chaotic stellar swarms, irregular and constantly colliding with neighbors, nothing like the organized structures we see today. But time changes everything. And as galaxies merged and grew, as they accumulated gas from their surroundings through filaments of the cosmic web, some began to spin, and spinning things naturally flatten. Just as pizza dough spreads outward when spun by a skilled chef, the gas in these rotating proto-galaxies settled into disks, and from these disks the spirals were born. The spiral arms themselves are not fixed structures like the blades of a fan, but patterns, density waves moving through the disk like ripples spreading across a pond. Gas clouds drift into these waves, experience increased density that triggers gravitational collapse and birth new stars. The massive blue stars born in these arms are short-lived. They illuminate the spiral pattern brilliantly with their intense radiation, but they burn out before completing even one orbit beyond the arm that spawned them. So the arms always look young, always look bright with the light of recently formed massive stars, while the spaces between the arms contain older, cooler, redder stellar populations that formed long ago and have drifted out of the spiral pattern. It is a cosmic illusion, a beautiful one, where the pattern persists even as the individual stars move through it, like waves on the ocean maintaining their form even though the water molecules move differently. By this calm era, spiral galaxies have perfected their architecture in ways that will endure for billions of years. Their disks reach equilibrium between the inward pull of gravity and the outward push of rotation, creating stable structures that can maintain their forms across cosmic ages. Spiral arms become well-defined and persistent, continuously regenerating themselves through the density wave mechanism, even as individual stars and gas clouds orbit through them. Many spirals develop central bulges, dense spheroidal concentrations of older stars at their cores, often surrounding supermassive black holes that lurk unseen at the gravitational center. Some spirals also develop bars, elongated structures of stars extending across their centers like cosmic axles, and these bars play crucial roles in channeling gas inward and regulating star formation rates in the inner galaxy. Our own Milky Way developed such a bar during this general epoch, a structure that continues to influence the dynamics of our galaxy today, affecting everything from star formation patterns to the orbits of stars throughout the disk. Now picture something entirely different. A smooth, featureless sphere of starlight with no spiral arms, no disk, no structure you can easily discern. This is an elliptical galaxy, and ellipticals form through a fundamentally different process, often through violence rather than gentle accretion. When two galaxies collide and merge, the gravitational forces during the collision scramble everything that was organized before. Pre-existing disks are disrupted, their careful balance between rotation and gravity destroyed. Stars scatter onto random orbits that no longer lie in a plane. Gas heats up through shocks and friction, triggering intense bursts of star formation that consume nearly all the available fuel in a cosmically brief period. What emerges from such cosmic collisions is smooth and three-dimensional, an ellipsoidal distribution of stars supported not by organized rotation like a spiral disk, but by the random velocities of billions of stars moving in all directions at once. Elliptical galaxies are often found in the densest regions of the universe, at the centers of galaxy clusters where mergers and interactions are most frequent. They have grown massive through successive mergers over billions of years, some accumulating trillions of stars and becoming the most massive single galaxies in the entire cosmos. These giant ellipticals are quiet now, most of their dramatic star formation long finished, settling into a slow evolution as their stellar populations age together. They are the retirement communities of the cosmic city, places where the excitement has passed and only the long, gentle decline toward dimness remains. Between these two extremes of spirals and ellipticals lie countless intermediate forms that testify to the complexity of galactic evolution. Lenticular galaxies possess disk-like structures similar to spirals but lack prominent spiral arms and contain little gas. Their star formation largely ceased. They represent a bridge between the actively star-forming spirals and the quiescent ellipticals, possibly spirals that have consumed or lost their gas reservoirs through environmental processes, or perhaps merger products that retained some memory of their progenitor's rotation even after the collision disrupted their spiral structures. Irregular galaxies, lacking any clear symmetrical structure, persist throughout this era as well, often representing smaller systems that have not yet undergone sufficient mergers to settle into a regular form, or systems recently disrupted by interactions with neighbors. The environment in which a galaxy resides plays a crucial role in determining its final morphology, creating a kind of cosmic segregation visible on the largest scales. In the densest regions of galaxy clusters, interactions with neighbors and with the hot intracluster gas conspire to transform spirals into lenticulars and ellipticals through various mechanisms. Gravitational encounters between galaxies, even those not resulting in actual mergers, can disturb spiral structures and strip away gas reservoirs through tidal forces. Ram pressure stripping, where a galaxy's motion through the hot intracluster medium sweeps away its cold gas, like wind removing leaves from a tree, can rapidly quench star formation and transform a spiral into what astronomers call a red and dead lenticular galaxy. Galactic harassment. The cumulative effect of repeated high-speed encounters with other cluster members can gradually heat a disk galaxy's stellar population, thickening the disk and destroying its delicate spiral structure over time. In contrast, galaxies in less dense environments, in small groups or in isolation in the cosmic voids, are more likely to retain their spiral structures. Here, the gas supply remains largely intact. Accretion of fresh gas from the cosmic web can continue feeding star formation, and mergers are less frequent and typically involve smaller, less disruptive partners. These field spirals can maintain steady star formation for billions of years, their morphology evolving more gently as they accumulate mass and refine their structures without the violent interactions characteristic of cluster environments. The supermassive black holes at the centers of galaxies, though tiny compared to the galaxies themselves, exert subtle but profound influences on galactic morphology during this epoch. The relationship between a galaxy's central black hole mass and its bulge properties, a tight correlation discovered by astronomers studying nearby galaxies, suggests a deep connection between black hole growth and galactic evolution operating through feedback mechanisms. During the merger events that create elliptical galaxies and build up bulges and spirals, material funnels into the galactic centers, feeding the black holes and triggering periods of energetic activity. The energy released by these active black holes in turn can heat and expel gas, regulating star formation and preventing the central regions from becoming too dense. This feedback process helps establish the final properties of galactic bulges and ellipticals, creating a remarkable correlation between structures operating on vastly different scales, from the event horizons of black holes to the extended distributions of stars in galactic bulges. By the end of the Calm Era, approximately 6 billion years after the Big Bang, the morphological segregation of the universe is well established, creating patterns that will persist for billions of years. The densest galaxy clusters have become dominated by red elliptical and lenticular galaxies, their stellar populations aging in unison, their colors gradually shifting toward the red end of the spectrum as their most massive stars evolve off the main sequence and only cooler stars remain. The less dense groups and field regions remain populated by blue spiral galaxies, actively forming new generations of stars, their colors reflecting the mix of old populations and young blue stars born recently in spiral arms. This color morphology relation, apparent in observations of galaxy clusters at various distances and thus various cosmic ages, tells the story of environmental influence on galactic evolution, showing how a galaxy's surroundings shape its destiny as much as its initial conditions. The process of galaxies settling into their final forms is not abrupt but gradual, proceeding over billions of years as structures relax and reach equilibrium. Many galaxies undergo their last major merger during this era, the final collision that establishes their ultimate morphology. After such events, the newly formed galaxy gradually relaxes, its stars settling onto stable orbits, its gas, if any remains, returning to the disk or being expelled entirely, its structure reaching a steady state that will endure. The diversity of galaxy morphologies that emerge during this era reflects the complexity and richness of cosmic evolution, with each galaxy's shape telling a story about its formation, history, environment, and the balance between various physical processes. The smooth ellipticals speak of violent mergers and consumed gas reservoirs, of dramatic star formation episodes followed by quiet aging. The elegant spirals reveal ongoing accretion and stable rotation of gas supplies maintained across billions of years, allowing sustained star formation. The intermediate lenticulars hint at environmental quenching and transformation, at galaxies whose gas was removed by their surroundings before they could finish their evolution. Together, they create a cosmic taxonomy, a classification of forms that helps us understand the processes shaping galactic evolution. This is the universe breathing slowly, finding balance, establishing structures that will persist, creating a stable framework within which smaller scale processes can unfold. The shapes that galaxies assumed during this calm era would prove remarkably durable, changing only slowly in response to minor mergers, gas accretion, or environmental effects. Once established, morphology persists, and the universe has entered a state of morphological maturity, where the primary architectural forms of cosmic structure are set and will endure throughout the long eras ahead. Nothing in the universe is alone, and gravity sees to that with patient inevitability. As the cosmos expands and evolves during the calm era, galaxies begin gathering into families through processes that operate on the largest scales imaginable. Groups, clusters, and even enormous superclusters form, creating a web-like architecture that will define the large-scale structure of the universe for all time to come. This assembly happens quietly and patiently, unfolding over billions of years as gravity draws matter together across vast distances. Imagine dark matter, invisible and pervasive, forming threads and filaments across the universe like a cosmic spider's web stretching across hundreds of millions of light years. At the nodes where filaments intersect, matter accumulates in the deepest gravitational potential wells in the cosmos. And into these wells, drawn by inexorable gravity, galaxies fall. Hundreds of them, sometimes thousands, drawing together over billions of years, bound by their mutual gravitational attraction into structures we call galaxy clusters, the largest gravitationally bound objects in the entire universe. During the calm era, galaxy clusters grow primarily through two processes that proceed at different rates and produce different effects. The first is hierarchical assembly through continuous accretion, where individual galaxies and smaller groups fall in from the surrounding cosmic web relatively gently. Galaxies traveling along the filaments encounter the cluster's gravitational pull and begin a slow infall, gradually spiraling inward over hundreds of millions of years. As they fall, they encounter the cluster environment in all its complexity, the hot intracluster medium, the gravitational influences of other cluster members, the overall tidal forces of the cluster's deep gravitational well. These encounters transform the infalling galaxies in profound ways. The hot intracluster medium that pervades galaxy clusters is one of the most remarkable features of these systems, initially surprising to astronomers who discovered it through X-ray observations. Heated to tens of millions of degrees by the gravitational energy released during the cluster's formation, this diffuse gas shines brightly in X-rays, often outshining the combined starlight of all the cluster's galaxies. The gas is ionized, its electrons stripped from their atoms by the extreme temperatures, and it exists in a tenuous but significant state, with a density far lower than any laboratory vacuum, yet containing more mass than all the cluster's visible galaxies combined. When galaxies fall into this hot atmosphere, they experience RAM pressure stripping, a process analogous to wind resistance, but operating on galactic scales. As a galaxy moves through the intracluster medium, the hot gas exerts pressure on the galaxy's own cold gas reservoirs, and for galaxies falling at high speeds, this pressure can exceed the gravitational force holding the galaxy's gas in place. The cold gas is swept away, stripped from the galaxy and left behind in a tail, extending behind like a comet's tail. Sometimes visible in radio observations showing trails of star formation or glowing hydrogen marking the galaxy's path through the cluster. Over time, this process transforms gas-rich spiral galaxies into gas-poor lenticulars, contributing to the morphological segregation characteristic of cluster environments. The dynamics of galaxy clusters during this era follow patterns that can be described using the physics of gravitating systems, with galaxies orbiting within the cluster's gravitational potential at velocities typically ranging from hundreds to over 1,000 kilometers per second. These high velocities, first measured spectroscopically by astronomers like Fritz Zwicky in the 1930s, were surprisingly large and indicated that clusters contained far more mass than could be accounted for by their visible galaxies and gas. This was among the first strong evidence for dark matter, the invisible mass that dominates the gravitational field of clusters and indeed of the universe as a whole. The structure of a typical massive galaxy cluster during the calm era resembles a cosmic city with distinct regions and populations arranged hierarchically. AAT8, the center, resides the dominant galaxy, usually a massive elliptical that has grown through mergers and the gradual consumption of smaller cluster members over billions of years, a process sometimes called galactic cannibalism. This central galaxy often hosts a supermassive black hole actively feeding on surrounding matter, making it a radio source detectable across cosmic distances. Surrounding the central galaxy, the cluster core contains a dense concentration of predominantly elliptical and lenticular galaxies, moving on complex orbits through the deep gravitational potential well, occasionally passing close enough for tidal interactions, but rarely colliding directly due to the vast distances between them. Beyond the core, the cluster's outer regions contain a more diverse mix of morphologies, with more spirals surviving toward the periphery, where environmental effects are less severe and galaxies retain more of their primordial gas content. Galaxy clusters do not exist in isolation, but are connected to one another through the filamentary structure of the cosmic web, those vast threads of dark matter and galaxies stretching across hundreds of millions of light years. Along these filaments, galaxies and groups travel in coherent streams, following the gravitational pull toward the nearest major cluster, creating patterns of flow on the largest scales. At the scale of hundreds of millions of light years, the pattern of clusters and filaments creates a stunning tapestry, a cosmic web of light and dark matter, with clusters marking the bright nodes and filaments connecting them across the voids. This structure, predicted by computer simulations of cosmic evolution and confirmed by large galaxy surveys, represents the largest organized structures in the universe, reflecting the primordial patterns imprinted during the first moments after the Big Bang, when quantum fluctuations were stretched to cosmic scales by inflation. The assembly of superclusters, the largest gravitationally connected structures, proceeds during this era through the gradual aggregation of clusters along extended regions of the cosmic web. A supercluster is not a bound structure like a galaxy or galaxy cluster in the strict sense, because the universe's expansion driven by dark energy is too strong for gravity to ever bind such enormous volumes of space. Instead, superclusters represent overdense regions where multiple clusters formed in relative proximity, connected by filaments and sharing correlated motions, but destined to continue separating as universal expansion carries them apart over billions of years. The most famous supercluster, the one containing our own Milky Way, would later be named Laniakea, meaning immense heaven in Hawaiian, encompassing roughly 100,000 galaxies spread across 500 million light-years, with the Milky Way residing at its outer edge. During the calm era, the growth rate of clusters begins to slow compared to earlier epochs when structure formation proceeded more rapidly. The most rapid phase of cluster assembly occurred earlier, during the universe's first few billion years, when matter was denser and gravitational attraction stronger relative to the expansion of space. By the time the universe reaches 3 to 6 billion years old, many clusters have already assembled most of their mass and are entering a phase of more gradual growth. New galaxies continue to fall in from the surrounding web, and smaller groups merge with larger clusters, but the dramatic collisions between major clusters become less frequent. The universe's accelerating expansion, driven by the mysterious dark energy that comprises about 68% of the total energy density of the universe, means that the largest scales are beginning to freeze out. Structures separated by cosmological distances will never merge, and even the growth of existing clusters will eventually cease as expansion carries their surrounding reservoirs of matter beyond gravitational reach. The physics of cluster mergers, when they do occur, is spectacular and profound, involving processes operating on scales from individual galaxies to the entire cluster system. When two galaxy clusters collide, an event that unfolds over hundreds of millions of years, the galaxies themselves rarely collide directly, because space within clusters remains so vast that galaxies pass through each other like two swarms of bees interpenetrating. But the hot intracluster gas, being a fluid, experiences violent shocks and heating as the two clusters' atmospheres collide and merge. These merger shocks can heat the gas to even higher temperatures, creating spectacular X-ray emissions and generating turbulence that will take billions of years to dissipate. The dark matter halos of the two clusters, detectable only through their gravitational lensing effects on background light, pass through each other relatively unimpeded, since dark matter interacts only through gravity, eventually merging into a single larger halo. Observations of such merging clusters, like the famous bullet cluster discovered through careful study of gravitational lensing and X-ray emissions, provide some of the strongest evidence for dark matter's existence and demonstrate its separation from ordinary matter during collisions. The environmental effects within galaxy clusters extend beyond just affecting galaxy morphologies, influencing the pace of galactic evolution, the colors and stellar populations of cluster galaxies, and even the properties of smaller satellite galaxies orbiting larger cluster members. Galaxies and clusters age faster, in a sense, than their counterparts in the field, their star formation quenched earlier, and their stellar populations evolving more rapidly toward older redder states. This environmental acceleration of galaxy evolution creates clear distinctions between cluster galaxies and field galaxies, observable across billions of years of cosmic history. Rich galaxy clusters during this era also serve as cosmic laboratories where the interplay between gravity, gas dynamics, and dark matter can be studied through multiple complementary observations. The distribution of mass within clusters, inferred from the velocities of galaxies measured spectroscopically, the temperature profile of the hot gas measured in X-rays, and gravitational lensing measurements of how background light is distorted by the cluster's mass, reveals the properties of dark matter halos on the largest scales. The balance between gravitational collapse and gas pressure support demonstrates fundamental physics in action on cosmic scales. The mixing of metals, heavy elements produced in stars and distributed through supernova explosions and stellar winds, into the intracluster medium chronicles the history of star formation throughout the cluster and demonstrates the mechanisms by which stellar products can be transported far beyond individual galaxies. The calm growth of galaxy clusters during this era establishes the large-scale structure that will characterize the universe for billions of years to come. The hierarchical pattern of galaxies in groups, groups in clusters, and clusters in superclusters, all connected by the filamentary cosmic web, emerges clearly by the end of this period. This structure is remarkably stable in its overall form, and once a galaxy joins a cluster, it typically remains bound for the rest of cosmic history, its orbit within the cluster gradually decaying through dynamical friction until it might eventually merge with the central galaxy, but never escaping back into the field. Similarly, clusters that have formed by this era persist as identifiable structures, gradually accreting more members but retaining their fundamental identity, their positions in the cosmic web established for eons to come. From a cosmic perspective, the assembly of clusters represents the last stage of significant structure formation at the largest scales. Larger structures like superclusters are not gravitationally bound and will never complete their collapse into single objects. Smaller structures, like galaxies themselves, have mostly formed by this point and are gathering into clusters. The calm growth of galaxy clusters thus marks the transition from a universe still actively assembling its major structures to one where the overall architecture is established, and subsequent evolution consists primarily of refinement and aging within the framework already created. This establishment of stable, long-lasting structure is a defining feature of the calm era, the period when the universe shifted from construction to habitation, from chaos to order, from becoming to being. Let yourself float now in the space between clusters, in one of the vast cosmic voids where galaxies are rare and dark matter tenuous and the density far below average. Even in this emptiness, you are not truly alone, for the cosmic microwave background surrounds you. That ancient light from the Big Bang, now cooled to just a few degrees above absolute zero, and the expansion of space itself gently stretches everything. And far in the distance, in every direction you might look, clusters of light shine, families of galaxies gathering together in the cosmic web, the universe having found its structure, and in that structure stability, and in that stability time for complexity to emerge. At the heart of nearly every mature galaxy, something sleeps. Not truly sleeping, but quiet now, patient in ways difficult for us to comprehend. A supermassive black hole resides there, containing millions, or sometimes billions of times the mass of the Sun, compressed into a region smaller than our solar system, warping space-time around itself in ways that defy intuition. These are the hidden anchors of galaxies, invisible yet profoundly influential. In the early universe, they blazed as quasars, among the most luminous objects in all of creation, devouring enormous quantities of matter and converting it into energy through the release of gravitational potential as materials spiraled inward. The gas spiraling toward these black holes formed accretion disks, heating to millions of degrees through friction and gravitational compression, shining brilliantly across the electromagnetic spectrum from radio waves to X-rays. Jets of particles, accelerated to nearly the speed of light by magnetic fields, threading the inner accretion disk, shot outward along the black hole's rotation axis, sometimes extending millions of light years into intergalactic space in displays of cosmic power that could be detected across the universe. The universe's adolescence was the age of brilliant quasars, when black holes fed voraciously and announced their presence across cosmic distances. But now, during this calm era, quiet descends upon the galactic centers. The transition from blazing quasar to quiet black hole is driven by simple physics. Black holes need fuel to shine, and matter must reach the galactic nucleus before it can be consumed. In the chaotic early universe, when galaxies frequently merged and collided, feeding material to central black holes was relatively easy. Galaxy mergers funnel gas inward through gravitational torques, breaking the angular momentum barrier that normally prevents material from falling into the center, providing fresh fuel for black hole growth and triggering episodes of intense accretion and quasar activity. But as galaxies mature and major mergers become less frequent, and as gas reservoirs are progressively converted into stars or expelled by feedback processes, the supply of fuel reaching galactic centers dwindles dramatically. The quasars dim, not because the black holes disappear or shrink, but because they simply run out of food. The black holes remain, still massive and hungry, but now they enter what we might call a gentle retirement, a phase of patience and occasional feeding rather than constant consumption. This doesn't mean they disappear from relevance or become mere relics. Even when not actively accreting significant amounts of matter, a supermassive black hole's gravitational influence extends throughout the galactic center and beyond. The black hole's mass, though tiny compared to the whole galaxy, typically only about 0.1% of the mass of the galactic bulge, dominates the gravitational field in the innermost regions, affecting stellar orbits and dynamics in profound ways. Stars in the nuclear star cluster, that dense concentration of stars surrounding the black hole like courtiers around a hidden monarch, follow complex orbits determined by the black hole's gravity. The closest stars complete their orbits in just years or decades, stellar speedways compared to the Sun's leisurely 230 million year orbit around the Milky Way center. In our own Milky Way, patient observations of stars orbiting the galactic center have provided perhaps the most compelling evidence for a supermassive black hole's presence. By tracking the positions of stars in the central light year over many years using advanced telescopes, astronomers mapped their orbits and found that they were ellipses centered on a radio source called Sagittarius, A*. The short orbital periods of the closest stars, one star completes its orbit in just 16 years, and their extraordinarily high velocities, reaching over 5,000 kilometers per second at closest approach, require a central mass of approximately 4 million solar masses concentrated in a region smaller than Mercury's orbit around the Sun. Yet no significant light emanates from this location beyond a faint radio and X-ray glow produced by small amounts of accreting material trickling onto the black hole. The only object that could contain such enormous mass in such a small volume without producing more light is a black hole. And this reasoning has been confirmed by similar observations in numerous other galaxies. There exists a mysterious relationship between supermassive black holes and their host galaxies, hinted at by various observations, and suggesting a deep fundamental connection between black hole growth and galactic evolution. The discovery that black hole mass correlates tightly with properties of the host galaxy's bulge, particularly the stellar velocity dispersion, which measures how fast stars move randomly within the bulge, indicates that black holes and galaxies grew together in some coordinated fashion over cosmic time. This relationship, known as the M-sigma relation, cannot be merely coincidental. It implies that processes occurring on vastly different scales, from black hole event horizons spanning light hours to galactic bulges spanning thousands of light years, are somehow linked through feedback mechanisms that couple their evolution. The mechanism creating this link involves what astronomers call active galactic nucleus feedback, the process by which energy released during black hole accretion affects the surrounding galaxy in ways that regulate further growth. When a black hole actively accretes matter, the energy released, sometimes approaching the theoretical maximum efficiency of converting matter to energy, far more efficient than nuclear fusion, can drive powerful winds and jets that heat, expel, or redistribute gas in the galaxy's central regions. This feedback can regulate star formation by preventing gas from cooling and condensing into stars, can prevent too much gas from accumulating in galactic centers, and can establish a self-regulating cycle that determines both the final black hole mass and the properties of the surrounding bulge. During major mergers that funnel gas into galactic cores, triggering both intense starbursts and rapid black hole growth, this feedback becomes particularly important and may explain why galaxy spheroids and black holes show such tight correlations in their properties. Beyond the calm era, most supermassive black holes have grown to masses roughly proportional to their host galaxy's bulge mass, having reached a quasi-equilibrium state where feedback from accretion prevents further rapid growth. The black holes in giant elliptical galaxies at the centers of clusters have become truly enormous, some reaching billions of solar masses, having grown through both gas accretion during the galaxy's formation and through direct mergers with other black holes as galaxies collided and merged. The supermassive black holes in spiral galaxies tend to be less massive, reflecting the smaller bulge masses of these systems, though still typically ranging from millions to hundreds of millions of solar masses. The detection and study of these quiet black holes requires clever observational techniques since, unlike their quasar ancestors, they produce little radiation from accretion. Instead, astronomers infer their presence through their gravitational effects on surrounding matter, a method called dynamical measurement. By measuring the velocities of stars or gas orbiting close to the galactic center using spectroscopy, applying Kepler's laws of orbital motion and solving for the mass required to produce those observed velocities at those distances. Astronomers can detect and measure supermassive black holes even when they are not actively feeding and producing electromagnetic radiation. This technique has confirmed that black holes are indeed present in galaxy after galaxy, from the smallest bulge-bearing systems to the largest ellipticals, establishing their ubiquity and fundamental importance to galactic structure. Occasionally, a quiet black hole experiences a brief feeding event that provides glimpses of its continued presence and reminds us that the monster still lurks at the center. When a star ventures too close to a supermassive black hole, approaching within what's called the tidal disruption radius, tidal forces, the difference in gravitational pull between the star's near and far sides, can overcome the star's self-gravity and literally tear it apart in a process called tidal disruption. This produces a temporary flare lasting months to years as stellar debris spirals into the black hole, briefly illuminating the normally quiet nuclear sound, allowing astronomers to study accretion processes in detail. Similarly, the accumulation of gas from normal stellar evolution, material lost from red giant stars in the nuclear star cluster through stellar winds, can provide a steady trickle of fuel, maintaining low-level accretion that keeps some black holes in a dim but detectable active state. The jets produced by actively feeding black holes, even in their quieter phase during the calm era, have significant impacts on their environments that extend far beyond the immediate vicinity. In galaxy clusters, jets from the central black hole in the dominant, elliptical galaxy inject enormous amounts of energy into the surrounding hot intracluster medium through a process that operates like a cosmic heating system. These jets create cavities or bubbles in the hot gas, regions of relativistic particles pushing aside the thermal plasma, visible as dark regions in X-ray observations, surrounded by bright shells of compressed gas. The energy deposited by these jets helps heat the cluster gas, counteracting radiative cooling that would otherwise cause gas to condense toward the cluster center. This feedback mechanism is crucial because without it, the hot gas in cluster cores would cool and condense, forming stars at rates far exceeding observations, the so-called cooling flow problem that puzzled astronomers for decades until the role of black hole feedback was recognized. The role of black holes as anchors and stabilizers of galactic structures becomes increasingly apparent as the calm era progresses. A massive central black hole stabilizes the innermost regions of a galaxy through its gravitational influence, preventing bars or spiral structures from extending all the way to the nucleus. The energy released during even modest accretion episodes helps regulate cooling flows and star formation in galactic centers. The tight correlations between black hole properties and galaxy properties suggest that black holes are not mere passengers in galactic evolution, but active participants, their growth and feedback processes intimately connected with the formation of the galaxies themselves. Interestingly, not all galaxies host supermassive black holes of equal size relative to their stellar mass, and these variations tell stories about galactic history. Galaxies that experienced major mergers tend to have more massive black holes relative to their stellar content, having both assembled more mass in violent events that efficiently funneled gas to the center and directly merged their progenitor black holes. Spiral galaxies that grew more quiescently through steady gas accretion and minor mergers tend to have less massive black holes relative to their total stellar mass, though they still follow the general scaling relations that connect black hole mass to bulge properties. As the calm era progresses, supermassive black holes across the universe gradually settle into their long-term quiet state, a retirement that will last for billions of years. The era of dramatic quasar activity is largely over, though individual black holes will occasionally flare when circumstances provide fresh fuel. The universe's active galactic nucleus population transitions from high luminosity quasars to lower luminosity active galaxies, reflecting the decreasing average feeding rates. The total energy output from supermassive black holes decreases, and their role shifts from dramatic disruptive actors to subtle stabilizing influences at the hearts of mature galaxies. Yet these quiet black holes remain formidable objects beyond our everyday comprehension. They contain the mass of millions or billions of suns, compressed to densities and conditions beyond human experience. An AT event horizon, the boundary from which not even light can escape. Space-time itself is warped beyond recognition, creating a region where the normal rules of physics break down in ways we're still working to understand. Within the event horizon, all paths through space and time led inexorably inward to the singularity, the point of infinite density and infinite gravity at the black hole's mathematical center, where our current theories of physics fail and quantum gravity, effects we cannot yet describe, become dominant. Let yourself approach a supermassive black hole now in imagination, not too close, but near enough to feel its presence warping space-time around you. Space itself curves in response to the black hole's mass, and time dilates, flowing more slowly the closer you get to the event horizon in a relativistic effect that would allow you to watch the universe age rapidly, if you could somehow hover near the edge and look outward. These objects, formed in the chaotic early universe and grown through billions of years of feeding and mergers, have become permanent features of cosmic structure. Their presence testifies to gravity's power to concentrate matter and energy to extremes, and their quiet state during this calm era signals that the universe has entered a calmer, more stable epoch, where violent accretion is no longer the norm but the exception. The supermassive black holes sit patiently at galactic centers now, hidden anchors maintaining gravitational order, occasionally flickering to life when circumstances allow, but mostly dark and patient and waiting, having transitioned from engines of chaos to keepers of balance in the cosmic order. Something is happening quietly across the cosmos, gradually and invisibly, but with profound implications for everything that will follow. The universe is changing in ways you cannot see with your eyes alone. But these changes matter more than almost anything else in the story of cosmic evolution. The cosmos is becoming chemically rich, and with each stellar generation, the proportion of elements heavier than hydrogen and helium increases, slowly transforming the cosmic inventory from the simple primordial mixture produced in the Big Bang to a richer, more complex chemistry capable of building rocky planets, complex molecules, and eventually the biochemistry of life itself. This enrichment is one of the most consequential transformations of the cosmic dark age and the eras that follow, laying the groundwork for worlds and oceans and atmospheres and all the complexity that might emerge from them. The universe emerged from the Big Bang with astonishing chemical simplicity, approximately 75% hydrogen by mass, 25% helium, and only trace amounts of lithium and beryllium. That's all. Everything else, every element that makes our world and our bodies, every carbon atom in every organic molecule, every oxygen atom in every water molecule, every iron atom in our blood, had to be created afterward, forged in stellar furnaces over billions of years, and distributed through space by stellar winds and supernova explosions in a process we call stellar nucleosynthesis. The process is elegant and patient, operating through nuclear fusion in stellar cores, where temperatures and pressures reach extremes impossible to recreate on Earth. Inside stars, nuclear fusion proceeds through a series of reactions that build progressively heavier elements. Hydrogen fuses to helium through the proton-proton chain in stars like the Sun, or through the CNO cycle in more massive stars. In more massive stars that reach higher core temperatures, helium fuses to carbon and oxygen through the triple alpha process, a reaction requiring 3 helium nuclei to come together simultaneously. Further fusion in the most massive stars creates neon, magnesium, silicon, sulfur, and eventually iron through a complex network of nuclear reactions proceeding in shells around the stellar core. Iron is special in this sequence, marking a boundary in stellar nucleosynthesis. Elements lighter than iron release energy when fused together. This energy release is what powers stars, providing the outward pressure that supports them against gravitational collapse. But fusing iron into heavier elements consumes energy rather than producing it, making such reactions thermodynamically unfavorable under normal stellar conditions. Iron accumulates in the cores of massive stars like ash in a furnace, unable to fuse further, building up until the core becomes so massive that electron degeneracy pressure can no longer support it, and catastrophic collapse ensues. Supernovae are the alchemical crucibles of the universe, the primary mechanism for distributing heavy elements and for creating elements beyond iron through processes impossible in stable stars. When a massive star's iron core collapses, it releases an enormous burst of gravitational energy, about 100 times all the energy the star produced through nuclear fusion during its entire lifetime, released in a matter of seconds. This energy drives the explosion of the star's outer layers at speeds reaching tens of thousands of kilometers per second, creating powerful shockwaves that sweep through the ejected material. In the extreme conditions within and behind these shockwaves, where temperatures momentarily exceed those in any stellar core and neutron densities become enormous, nuclear reactions proceed with extraordinary rapidity, building elements all the way up to uranium and beyond through various processes, including rapid neutron capture. The explosion scatters these newly forged elements across vast regions of space, mixing them with the surrounding interstellar medium in beautiful glowing nebulae that can be observed for thousands of years after the explosion, enriching the cosmic inventory for the next generation of star formation. Beyond the calm era, multiple generations of stars have lived and died across the universe, each contributing to the growing inventory of heavy elements in a process that proceeds at different rates in different environments, but everywhere moves in the same direction toward greater chemical complexity. The interstellar medium, the gas and dust between stars that fills the space within galaxies, has been progressively enriched with the products of stellar evolution. When new stars form from this enriched gas, they incorporate these heavy elements into their composition from the very beginning of their existence, becoming what astronomers classify as population to of stars with moderate metallicity found in globular clusters and galactic halos, or population I stars with the highest metallicity found in galactic disks where star formation continues actively. Our own Sun, formed about 4.6 billion years ago from a molecular cloud already enriched by previous generations, is a population I star, and its composition reflecting multiple generations of prior stellar evolution means that approximately 1.5% of its mass consists of elements heavier than helium, a small fraction, but vastly more than the nearly zero metallicity of the universe's first stars. The pattern of chemical enrichment varies across the universe, creating a kind of cosmic geography of metallicity that tells stories about star formation history and environment. In regions where star formation has been most active and sustained over cosmic time, the dense cores of galaxy clusters, the disks of massive spiral galaxies, metallicity increases most rapidly as successive stellar generations build upon the chemical legacy of their predecessors. The hot intracluster medium in galaxy clusters becomes significantly enriched with iron, oxygen, and other elements ejected by supernovae in member galaxies, creating a metal-rich bath surrounding the galaxies with abundances reaching roughly 1/3 of solar values in the most enriched clusters. Within galaxies themselves, metallicity gradients develop naturally, with central regions becoming more enriched than outer regions, reflecting the higher star formation rates and more complete processing of gas in galactic cores, where stellar densities are highest and star formation has proceeded most vigorously. Different types of supernovae contribute different elements to the growing cosmic inventory in ways that leave distinctive signatures in abundance patterns. Type 2 supernovae, the explosions of massive stars that retained their hydrogen envelopes, produce primarily oxygen, neon, magnesium, and silicon, along with lesser amounts of many other elements through the burning of successive fusion shells during the star's lifetime and through explosive nucleosynthesis during the collapse. Type ER supernovae, thermonuclear explosions of white dwarf stars triggered when they accrete too much mass from a companion star and exceed the Chandrasekhar limit, produce primarily iron peak elements, iron, nickel, cobalt, and nearby elements in the periodic table through explosive carbon and oxygen burning. The relative contributions of these supernova types, combined with the contributions of lower mass stars through planetary nebulae and stellar winds, determine the detailed abundance pattern of elements in the interstellar medium, creating characteristic ratios that evolve with time and can be read like a history book by astronomers studying stellar populations. The increasing metallicity has profound consequences that extend far beyond simply adding new entries to the cosmic inventory of elements. Heavy elements fundamentally alter the processes of star formation, stellar evolution, and planet formation, creating feedback loops that influence the subsequent course of cosmic evolution in ways both obvious and subtle. When clouds of gas containing heavy elements collapse to form new stars, the presence of metals, as astronomers call all elements heavier than helium, allows the gas to cool more efficiently through additional radiative processes. Carbon, oxygen, and other elements can form molecules and dust grains that radiate away thermal energy more effectively than pure hydrogen and helium, which have limited cooling mechanisms. This enhanced cooling is crucial because it means that gas clouds can fragment into smaller pieces before collapsing, naturally leading to the formation of lower mass stars with longer lifetimes. The universe is learning, through pure physics and chemistry, how to make stars that will last billions or even trillions of years, rather than burning out in mere millions. The formation of dust grains, tiny solid particles composed of silicates, carbon compounds, and ice, is only possible in a metal-enriched universe. And though these grains comprise only about 1% of the interstellar medium by mass, they play an outsized role in cosmic evolution through multiple mechanisms. Dust absorbs ultraviolet and visible light from stars, re-radiating the energy as infrared radiation and helping cool star-forming clouds through this conversion. Dust grains serve as surfaces on which molecules can form through surface chemistry, catalyzing chemical reactions that would proceed very slowly or not at all in the gas phase, where molecules must find each other through random collisions. Simple molecules like molecular hydrogen and more complex ones like water, ammonia, methanol, and even organic compounds can form on dust grain surfaces in molecular clouds, creating a rich interstellar chemistry that becomes more complex with each passing epoch as metallicity increases. Most significantly, for the eventual emergence of life and for our own existence, dust grains in protoplanetary disks, those rotating disks of gas and dust surrounding young stars, serve as the fundamental building blocks of planets through a process that cannot occur without them. These microscopic grains stick together through electrostatic forces and gentle collisions, gradually growing from submicron particles to millimeter-sized pebbles, to centimeter-sized rocks, to meter-sized boulders, to kilometer-sized planetesimals, and eventually through continued accretion and collision to planets. Without heavy elements to form dust grains, this entire process of terrestrial planet formation would be impossible. The universe's first stars, formed from pristine hydrogen and helium, could not have had rocky planets orbiting them. Only later, after sufficient chemical enrichment, did Earth-like worlds become possible. By the Calm Era, chemical enrichment has proceeded to the point where the formation of terrestrial planets becomes not just possible, but common throughout the universe. The typical star-forming region during this epoch has a metallicity perhaps 1/3 to 1/2 that of the Sun, lower than our current solar neighborhood, but sufficient to build substantial rocky worlds with iron cores and silicate mantles. As the era progresses and more stars live and die, contributing their chemical gifts to the interstellar medium, metallicity continues to increase, reaching solar values and beyond in the most actively star-forming regions by the time the universe is 8 or 9 billion years old. This means that Earth-like planets, with differentiated structures including iron cores, silicate mantles and crusts, and the potential for water-rich surfaces, can form in abundance around the Sun, like stars being born during this golden age of cosmic chemistry. The chemical enrichment of the universe also enables the formation of complex organic molecules in space itself, not just on planetary surfaces, but in the cold darkness of molecular clouds where stars are born. In these dense molecular clouds, where temperatures hover only a few degrees above absolute zero, a rich chemistry unfolds, driven by ion molecule reactions, cosmic ray bombardment, and surface chemistry on dust grains. Carbon atoms incorporate into molecules, forming carbon monoxide, formaldehyde, methanol, ethanol, and progressively more complex organics, including molecules that are precursors to amino acids, the building blocks of proteins. Some of these molecules form in the gas phase through efficient ion-molecule reactions that proceed even at extremely low temperatures, while others form on dust-grained surfaces where hydrogen atoms landing on the grains can progressively add to other atoms, building up molecular complexity through surface reactions. When stars form from these enriched molecular clouds, some of these organic molecules survive on dust grains incorporated into the protoplanetary disk, becoming part of comets and asteroids, and eventually through impacts delivered to planetary surfaces where they may contribute to prebiotic chemistry. Different galaxies experience different chemical enrichment histories depending on their star formation histories, their masses, and their environments, creating diversity in the cosmic chemical landscape. Giant elliptical galaxies, which formed most of their stars in intense early bursts during their violent assembly through mergers, reached high metallicities quickly and then evolved chemically very little afterward as star formation ceased. Their stellar populations, though old, are relatively metal-rich compared to their ages, reflecting the efficient processing of gas during their formation epoch. Spiral galaxies, with their ongoing star formation in disk regions, show steadier, more gradual enrichment over cosmic time, with metallicity increasing approximately linearly with time as successive generations of stars enrich the interstellar medium in a process that continues to this day. Their stellar populations show correlations between age and metallicity, with older stars generally having lower metal content than younger stars, though with considerable scatter due to radial mixing and other dynamical processes. Dwarf galaxies, the smallest galaxies containing only millions to billions of stars, evolve chemically more slowly than their massive counterparts due to their shallow gravitational potential wells. Their weak gravity means that energetic supernova explosions can expel significant fractions of their gas into intergalactic space, carrying away heavy elements freshly synthesized in the supernova and reducing the efficiency of chemical enrichment within the galaxy. This makes dwarf galaxies chemically primitive relative to massive galaxies of the same age, a difference observable in their stellar populations and gas phase abundances. This variation in enrichment efficiency across different galaxy masses creates a mass metallicity relation, with more massive galaxies achieving higher metallicities at any given cosmic time. A relationship that holds from the smallest dwarf galaxies up to the most massive ellipticals. The distribution of different elements also tells detailed stories about stellar evolution and nucleosynthesis processes that produce them. The ratio of oxygen to iron, for example, provides information about the relative contributions of massive stars, which produce primarily oxygen, and type Ia supernovae, which produce primarily iron. Because type Ia supernovae arise from white dwarfs that take time to accrete mass from companions before exploding, typically hundreds of millions to billions of years, they contribute to chemical enrichment on longer timescales than massive stars which explode as supernovae within millions of years of their formation. This temporal difference creates characteristic patterns in abundance ratios that vary with time and environment, patterns that astronomers can read like a detailed history book, decoding the star formation and chemical evolution history of galaxies from the abundances measured in their stars and gas. Elements heavier than iron, including precious metals like gold and platinum and radioactive elements like uranium and thorium, require special circumstances for their formation beyond what occurs even in normal supernovae. long thought to be produced primarily in core collapse supernova explosions through rapid neutron capture in the extreme conditions of the collapsing core and subsequent explosion. Recent research, including gravitational wave detections and electromagnetic follow-up observations, has revealed that neutron star mergers, collisions between two neutron stars orbiting each other in compact binary systems, may be the dominant source of these heaviest elements. During such mergers, matter is ejected at high velocities under conditions of extreme neutron richness, perfect for building heavy elements through the air process or rapid neutron capture process, where atomic nuclei capture many neutrons in rapid succession before having time to beta decay. These rare violent events distribute relatively small amounts of the heaviest elements per event, but over billions of years across the entire universe. They contribute significantly to the cosmic inventory of elements beyond iron, including much of the gold and platinum in the universe. By the end of the calm era, the universe's chemical composition has been fundamentally transformed from its primordial simplicity. The interstellar medium in star-forming galaxies has been enriched to perhaps 1/3 to 1/2 solar metallicity on average, with the most enriched regions approaching or exceeding solar values. This means that roughly 1 out of every 50 to 100 atoms is now something other than hydrogen or helium. Still a tiny fraction when stated this way, but sufficient to fundamentally change cosmic evolution and open entirely new possibilities. Rocky planets can form in abundance. Organic chemistry can develop both in space and on planetary surfaces. The ingredients for life, carbon, nitrogen, oxygen, phosphorus, and sulfur, the so-called cyanops essential for biochemistry as we know it, are present in appreciable abundance throughout star-forming regions. The universe has become chemically capable of complexity in a way that the early universe, with only hydrogen and helium and traces of lithium, could never have been. This chemical enrichment represents a one-way transformation in cosmic evolution. Elements once created in stellar cores and distributed through space never revert to the hydrogen and helium from which they came. There are no natural processes that destroy heavy elements and return their nucleons to primordial form. The universe ratchets inexorably upward in chemical complexity, each stellar generation building upon the contributions of the previous, creating an ever richer cosmic environment with each passing billion years. This progression from simplicity to complexity, from uniformity to diversity, from hydrogen and helium to the full periodic table, is one of the most profound trends of cosmic evolution, as fundamental as the expansion of space or the formation of structure through gravitational collapse. And ultimately, it makes possible everything that follows in the cosmic story, including worlds and chemistry and life itself, connecting the nuclear fires inside stars to the eventual emergence of planets and perhaps biology through the patient accumulation of heavy elements across billions of years. A new kind of star appears across the cosmos during this calm era, neither the most massive nor the most numerous in the stellar census, but perhaps the most important for the unfolding story of complexity in the universe. Stars like our Sun begin to populate galaxies in significant numbers. G-type stars and their slightly smaller K-type cousins, stellar bodies with masses similar to the Sun that occupy a sweet spot in stellar evolution. These stars possess a gentle balance of properties that makes them ideal hosts for something remarkable, stable planetary systems that might harbor complex chemistry and perhaps even life. During this epoch, for the first time in cosmic history, sun-like stars become common throughout the universe, filling space with steady, reliable sources of energy that will burn calmly for billions of years, long enough for extraordinary processes to unfold on any worlds that might orbit them. The sun itself won't form for another few billion years, but stars very much like it are being born now in molecular clouds throughout countless galaxies, and these stellar pioneers establish the pattern that will make our own existence possible billions of years later. These sun-like stars possess several special qualities that distinguish them from both their more massive and less massive siblings in the stellar population. They burn calmly and steadily for approximately 10 billion years, a main sequence lifetime comparable to the current age of the universe itself, and vastly longer than the brief millions of years that massive stars enjoy. This longevity provides timescales long enough for remarkable things to happen on any planets orbiting nearby. Time for planetary systems to fully form and stabilize. Time for geological evolution to shape planetary surfaces and create atmospheres. Time for complex chemistry to develop in oceans or other liquid environments. And if conditions permit, time for the slow unfolding of biological evolution from simple to complex forms. Sun-like stars form through a well-defined process that by this calm era has become the standard mode of stellar birth in the disk regions of spiral galaxies, where active star formation continues. The process begins within giant molecular clouds, those vast reservoirs of cold gas and dust, stretching dozens or hundreds of light years across where turbulence, magnetic fields, and gravity interact in complex ways to create structure. Within these clouds, dense cores form in regions where gravity manages to overcome the supporting forces of turbulence and magnetic pressure, typically in the densest, darkest regions shielded from the ionizing radiation of nearby massive stars. As such a core begins to collapse under its own gravity, it fragments and rotates due to the conservation of angular momentum inherited from the turbulent motions in the larger cloud. This rotation causes the collapsing material to flatten into a disk with a central concentration that will become the protostar, creating the basic architecture that will later develop into a star surrounded by a planetary system. The protostar itself is initially dark and cool, merely a concentration of matter heated by gravitational compression, but not yet hot enough for nuclear fusion. Material from the surrounding disk continues accreting onto the protostar, spiraling inward through the disk and falling onto the growing stellar embryo, adding mass and increasing the central temperature and pressure with each new layer of accreted material. This accretion phase can last hundreds of thousands of years, during which the protostar grows and heats gradually, slowly approaching the conditions necessary for nuclear ignition. After sufficient mass has accumulated, the core temperature reaches approximately 10 million degrees Kelvin, hot enough to ignite sustained hydrogen fusion through the proton-proton chain reaction that will power the star for the rest of its main sequence lifetime. At this moment, a true star is born, entering the main sequence phase, where it will spend the vast majority of its existence fusing hydrogen into helium in its core while maintaining a stable balance between the inward pull of gravity and the outward push of radiation pressure and gas pressure generated by the fusion reactions. The remaining disk material surrounding the newborn star faces several possible fates. It can continue accreting onto the star, adding to its final mass. It can be blown away by strong stellar winds and radiation pressure, especially from the ultraviolet light of the young star. Or most interestingly, for the story of cosmic complexity, it can condense into planets, asteroids, and comets, forming a planetary system surrounding the newborn star. Sun-like stars possess several characteristics that make them particularly interesting from the perspective of habitability and the potential for complex chemistry and life. Their surface temperatures, typically between 5,000 and 6,000 degrees Kelvin, mean they emit most of their light in visible wavelengths, the same wavelengths that would later prove ideal for photosynthesis when life evolved that process on Earth, allowing efficient capture of stellar energy for biological processes. Their luminosity is moderate, bright enough to warm planets at reasonable orbital distances, but not so intense as to rapidly evaporate atmospheres through extreme heating or drive wildly unstable climate variations that would make the long-term evolution of complexity difficult. Their main sequence lifetimes of roughly 10 billion years are long enough for extremely slow processes like biological evolution to unfold over billions of years, yet not so long that they burn effectively unchanged for longer than the current age of the universe as the smallest red dwarfs do, which will continue fusing hydrogen for trillions of years into the far future. Perhaps most importantly for the potential emergence of life, Sun-like stars are remarkably stable over timescales of billions of years. They don't flare violently and unpredictably like small red dwarf stars, whose intense magnetic activity can produce stellar flares with energies far exceeding anything the Sun produces. Flares capable of stripping away planetary atmospheres or sterilizing surfaces with intense bursts of X-rays and ultraviolet radiation. They don't vary dramatically in luminosity, like some larger stars whose pulsations or eruptions might make planetary climates chaotically unpredictable over timescales of years to millennia. Instead, Sun-like stars burn steadily and calmly, their energy output varying by less than a fraction of a percent on timescales of days to years, though there is a gradual secular increase in luminosity over billions of years as the helium ash accumulating in the core slightly changes the star structure. This stability creates ideal conditions for any planets orbiting such stars, constant reliable energy input maintained over billions of years, moderate radiation environments that don't threaten atmospheric or surface chemistry with destructive bursts, and temporal consistency extending across timescales longer than the entire history of complex life on Earth, allowing slow evolutionary processes to proceed without catastrophic interruptions from the host star's variability. By the middle of the calm era, Sun-like stars are being born throughout the universe wherever active star formation continues in spiral galaxy disks and in the star-forming regions of irregular galaxies. In the spiral arms of galaxies like the young Milky Way, stellar nurseries produce these stars alongside their more massive blue siblings that will live briefly but brilliantly, and their more numerous red dwarf cousins that will outlive everything else. The initial mass function, the statistical distribution of stellar masses at birth, naturally produces more lower mass stars than higher mass ones following a power law distribution. But Sun-like stars, though not the most numerous category, are common enough to populate galaxies with billions of such objects. In a large spiral galaxy, Sun-like stars might comprise roughly 5 to 10% of all stars born during any given epoch, which translates to billions of individual solar analogues spread throughout the galaxy, each potentially hosting its own planetary system. The planets that form around these sun-like stars represent one of the most significant developments in cosmic evolution during the Calm Era. For this is when the process of terrestrial planet formation becomes routine and Earth-like worlds begin appearing throughout the universe. Planet formation in protoplanetary disks around young stars follows a well-defined sequence of processes that build planets from microscopic dust grains over tens of millions of years. Dust grains in these disks, composed of silicates in the hot inner regions, and additionally of carbon compounds and water ice beyond the snowline, where temperatures are low enough for volatiles to condense, stick together through gentle collisions, aided by electrostatic forces and van der Waals forces operating on microscopic scales. These grains grow through this coagulation process, building up through a size progression from micrometers to millimeters to centimeters, and eventually to meter-sized objects through continued accumulation. Once objects reach roughly kilometer sizes, they are called planetesimals, small planetary building blocks with sufficient gravity to attract additional material gravitationally rather than relying only on random collisions. Planetesimals, once formed in sufficient numbers, grow through runaway accretion into planetary embryos, moon-sized to Mars-sized objects that represent an intermediate stage between planetesimals and full planets. These embryos continue to grow through giant impacts with other embryos and through accretion of remaining planetesimals, eventually merging over tens of millions of years to form the final planets of the system. The architecture of planetary systems varies considerably depending on details of the formation process, including disk mass, stellar mass, presence of turbulence, and timing of various stages, but certain patterns emerge that appear to be common. Systems typically contain several rocky terrestrial planets in their inner regions, orbiting within distances comparable to Venus's or Earth's distance from the Sun, formed from the refractory materials that can condense at the high temperatures in the inner disk. These terrestrial worlds, if they form in the right temperature range, neither so close to the star that surface water boils away, nor so far that water remains permanently frozen, can potentially maintain liquid water on their surfaces under appropriate atmospheric conditions. A zone astronomers would later call the circumstellar habitable zone, or sometimes colloquially the Goldilocks zone. Beyond the terrestrial planet region, gas giant planets often form in the cold outer regions of protoplanetary disks, massive worlds composed primarily of hydrogen and helium captured from the disk gas onto rocky icy cores that grew large enough quickly enough to gravitationally attract and hold the abundant light gases before the disk dispersed. These gas giants, analogous to Jupiter and Saturn in our solar system, can significantly influence the dynamics and evolution of their planetary systems through their strong gravitational effects on smaller bodies. The first Earth-like planets begin appearing during this Calm Era, rocky worlds with sizes similar to Earth, compositions dominated by silicates and iron, and orbital locations that place them in their star's habitable zone, where temperatures could potentially allow liquid water to exist on the surface given appropriate atmospheric conditions. These planets form through the accumulation processes described above over tens of millions of years, experience intense bombardment periods as the remaining planetesimals and smaller debris clear out of the system, and eventually settle into stable orbits where they will remain for billions of years, barring catastrophic encounters. Their formation requires the chemical enrichment we discussed earlier. Without substantial quantities of elements heavier than helium, there would be no rock, no metal, no solid material from which to build terrestrial planets. The calm era, with its increasing metallicity, resulting from multiple generations of stellar evolution and its abundant population of newly formed sun-like stars, represents the first period in cosmic history when Earth-like worlds can form in large numbers throughout the universe, potentially numbering in the billions in each large galaxy. The habitability of these early Earth-like worlds, their capacity to actually support life as we know it, remains an open question that drives much of modern astrobiology research, for having liquid water is necessary, but far from sufficient for habitability. To be habitable in the sense relevant to life, as we know, it requires several conditions beyond just the presence of liquid water. A planet needs sufficient mass to retain an atmosphere through gravitational binding over billions of years, but not so much mass that it captures hydrogen and helium from the protoplanetary disk and becomes a gas or ice giant rather than a terrestrial world. This restricts habitable planet candidates to a mass range roughly from half Earth's mass to perhaps twice Earth's mass. The planet needs geological activity to recycle elements between the surface and interior, to regulate climate through volcanism that replenishes atmospheric gases, and to drive tectonics that might concentrate nutrients and create diverse environmental niches. A magnetic field generated by a liquid metallic core helps shield the planet's surface from stellar wind and cosmic radiation that might otherwise strip away the atmosphere or deliver harmful doses of radiation to the surface. The planet needs a relatively stable orbit and climate over billions of years, which typically requires a nearly circular orbit and absence of large gravitational perturbations from other planets. And crucially, the planet needs the right chemical ingredients in sufficient abundance, liquid water as a solvent, carbon-based organic molecules as the basis for complex chemistry, energy sources to drive chemical reactions away from equilibrium, and various elements required for biological processes as we understand them. The planets forming around sun-like stars during the calm era have the potential to meet these conditions given fortunate circumstances. Their host stars provide stable moderate energy input maintained over billions of years. The increasing metallicity of the universe means chemical ingredients are abundant in the protoplanetary disks from which these planets form. The planet formation process can produce worlds of the right size and composition in the right orbital locations. Water, abundant in the outer regions of protoplanetary disks beyond the snowline, where it exists as ice, can be delivered to inner terrestrial planets through impacts by water-rich asteroids and comets originating from the outer system, potentially creating surface oceans on worlds that formed dry. Volcanic activity driven by radiogenic heating from long-lived radioactive isotopes like potassium-40 thorium-232, and uranium-238 can create atmospheres of nitrogen, carbon dioxide, and water vapor through outgassing. Lightning, ultraviolet radiation from the host star, and chemical energy from submarine hydrothermal vents can drive prebiotic chemistry that might eventually lead toward life. All the pieces are falling into place during this era, all the necessary ingredients and conditions assembling for the first time in cosmic history. But even if individual planets are potentially habitable with all the right initial conditions, they still need time, immense stretches of time, measured in billions of years, for complex processes to unfold from chemistry to biology to complex multicellular life. This is where the longevity of sun, like stars, becomes absolutely crucial to the story. Unlike massive stars that burn out in millions of years, far too quickly for biological evolution to proceed beyond perhaps the simplest stages, sun, like stars, will shine steadily for 10 billion years with relatively minor variations in their properties. This provides a vast temporal canvas spanning billions of years on which slow processes can develop without interruption. Chemical evolution can occur in planetary oceans, building from simple organic molecules delivered by comets or synthesized in the atmosphere toward increasingly complex molecular systems through countless cycles of reaction and selection. If life emerges through whatever processes lead from chemistry to biology, processes we still don't fully understand even in principle, it would have billions of years available to evolve from simple single-celled forms toward potentially complex multicellular organisms, perhaps even eventually toward intelligent species capable of understanding their place in the cosmos. The calm era thus represents a fundamental transition point in the universe's capacity for complexity and its potential to generate life. For the first time in cosmic history, all the necessary conditions for life as we know it are coming together in one package available simultaneously. Long-lived stable stars providing constant energy, rocky planets in habitable zones with stable orbits, chemical enrichment providing the necessary elements for both planet formation and complex chemistry, liquid water potentially available on planetary surfaces, and billions of years of stability for slow processes to develop without catastrophic interruption. Whether life actually emerges on any of these early worlds, whether the transition from complex chemistry to self-replicating systems to metabolism to evolution actually occurs, remains unknown. We have no direct evidence one way or another about life on planets in this early era. But the stage is being set, the conditions are being established, and the vast experiment that might lead from chemistry to biology to intelligence is beginning to unfold across countless worlds, orbiting sun like stars throughout the universe during this golden age. The sun, like stars born during the calm era, some 9 to 12 billion years ago, remain with us today if they haven't yet evolved off the main sequence, still shining steadily on their long main sequence journeys across billions of years. These ancient G-type stars, enriched with heavy elements from previous stellar generations, but not as metal-rich as the Sun, formed billions of years later, orbit in the halos and thick disks of galaxies like the Milky Way. They represent surviving witnesses to this earlier epoch, and their planetary systems, if any, remain intact after billions of years of dynamical evolution, might harbor ancient worlds that have been orbiting their stars since shortly after those stars formed in the cosmic dawn of sun like stellar populations. In a very real sense, the calm era's legacy of sun, like stars, and their potential planetary systems extends directly into the present day and into our own existence, connecting us across time to that earlier era when the universe first became truly capable of fostering the long-term stability and chemical richness that complex systems like life require.